Hello, and welcome to this new tutorial series for first year physicists on philosophy of physics. So you guys are all here for a variety of reasons. You're all interested in science, and you all have a decent understanding of maths and logical thinking. Rather than the content of science, today what we're going to be talking about is the nature of science. We're going to be looking at how science works, how scientific thought has evolved over the years and centuries. Now, you might not be used to this sort of discussion, this sort of conversation, but what you're learning right now, we think is vital for your future career as a scientist. By doing a physics degree or a degree in science, you're learning to use some extremely powerful tools. And it's really important that we have a discussion about the responsibilities we have when taking those into society. So, we're going to start with some important concepts underpinning the theory of knowledge itself, or epistemology, as that's known in philosophy. Then we're going to have some interviews with a theoretical or computational physicist, me. We're going to have some interviews with an experimental physicist and a philosopher. We're going to see what different approaches each of those people take to science and the scientific method. We're going to look at some examples of scientific discoveries and thoughts in history and how these things all relate to each of those people. And finally, we're going to give you, students, some questions, some discussion prompts to have in your tutorials to discuss these ideas with your tutors. So one of the ways that we might think about science and knowledge itself is this idea that the equations that we learn represent a fundamental structure of the universe. So these ideas, known as rationalism, to me, rationalism is more that the equations that I use when I'm doing science represent this fundamental nature of the universe that is somehow real. So empiricism is often seen as a rival school of thought to rationalism. Empiricists believe that observation is the source of knowledge. And then maths, those fundamental equations, just become a tool, a model to describe the data that is around us. They're not real in their own right. Like a language, for example, I'm sat on this chair. The word chair describes this object in reality, but without this object in reality, that word chair means nothing. It's just a tool I'm using to describe observations around me. Scientists through the university programs are often encouraged to see the universe in an empiricist's perspective, to believe that data is fundamental to the scientific method. Okay, so as a scientist, I'm throwing these words around all the time. Empiricism, rationalism. What do they mean to you as a philosopher? What do these words mean to you?
So there's been an age-old rivalry between rationalists. So these are people who think that the best way to acquire knowledge about reality is by reflecting, by using our God-given reason and insight. Against empiricists, on the other hand, that have thought that we need to rely on sense experience, on the evidence that we see and that we feel around us, mediated with use of instruments like telescopes and microscopes. Rationalists in the sort of Middle Ages, people like René Descartes, were convinced that the senses were unreliable, right? That the existence of hallucinations and dreams meant that the things you see and the things you hear and whatnot can't be trusted, right? You can be wrong about those, whereas your own intellect, had a higher claim to sort of authority.
Yeah.
Whereas empiricists like John Locke and David Hume were like, no, what we need to be doing is experiments and gathering data and gathering evidence.
So while these ideas appear to be contradictory, both are key parts of the scientific method as we use it. Theory is often developed from rational arguments, and then it's tested against real-world experiments, which are used to refine that theory, make predictions, test against real-world experiments. Cyclical process. So what are we talking about when we're talking about the scientific method? I'm going to use an example from my own research to discuss this. Proteins and biological networks, it doesn't matter if you don't understand them right now. We'll learn about it as we go through. So here's some theory, here's some equations. Quite complicated equations, in a few years you'll know what they mean. But for now, I could take these equations and I could use them to program a computer simulation, which is what we're seeing right here of a biological network. The fact that these equations are there means we've got maths, we've got prediction, we've got deduction. This idea of rationalism we're talking about. And now if we make that 100,000 times bigger, we're talking about doing experiments. So that's a rheometer, something that measures how things move. And if we're taking evidence from that, we're talking about data, we're talking about analysis, we're talking about empiricism. But then we have the question of, how these things relate to one another. What even is science? So here's what I think my version of the scientific method is. And there isn't just one, but this is one of them. So we might observe something. We might then collect some evidence about that thing. We might then analyse that evidence. And then we might develop a theory. Now, you might think that the next step then is to build things, cameras, games, cars, vaccines, technology. But in terms of the scientific method, that's not the next step. The next step actually is to go straight back to that observe, collect some more evidence, analyse that evidence, develop a better theory, use that theory to predict some more observations, collect more evidence, analyse theory, observe evidence, analyse theory. This cycle leads to what we might call scientific knowledge. And that sort of cycle, that sort of path reminds me of a quote from one of my favourite authors, Brandon Sanderson. He says, "Journey before destination." The idea that the output of the scientific method is not as important as the process of performing science. It's the process, not the solution. It's about reducing uncertainty in those theories that we develop. And that's an important thing in the modern world. And you can start anywhere in this cycle and it never stops. It is a continuous process. So we might ask ourselves what scientists, economists, politicians, faith leaders, philosophers, Brian Cox, friends and family are even talking about when they use the word science. Let's discuss that.
Hi, I'm Tim Moorsom. I'm an experimental physicist and a lecturer in physics and engineering. So it's almost entirely theory-based. Really what we're trying to do through the course I teach is give students a foundational understanding of quantum mechanics through exploring Schrödinger's equation. So what we aim to do is provide some simplified examples where we can explore how that equation works and how it interacts with different problems, where there are exact analytical solutions. Well, it's actually very different to the research that I do. So I'm not actually a theoretician, I'm an experimentalist. So I work in a field called condensed matter physics, which is still very heavily influenced by the quantum mechanics that I teach. But when I'm teaching this, I'm generally focusing on simple single particle systems because they're much easier to understand in a classroom setting. The models that inform the experiments that I do are based on much more complicated multi-particle systems that don't have these exact analytical solutions. And actually, in some cases, I'm working with experiments that are based on empirical models, where what we've done is gathered data about how a particular system behaves, and then we've observed the outcome of experiments and devised a governing equation or a model that explains that output, even though the actual physics of the system might be a bit of a black box, and we don't necessarily know exactly what's going on yet. So when we're teaching, what we want to do is give students relatively simple models where they can follow all of the mathematical steps. What we don't want to be doing is presenting students with something very complicated where we're going to have to skip a lot of steps and they're just going to have to take our word for it. While what I'm teaching still gives foundational knowledge about quantum mechanics, it won't necessarily explore some of these more complex aspects. And it is important to try to link up what we're teaching to that more complex work that we do in research so that it has a real world basis. So even though what we're teaching is a relatively simplified version of quantum mechanics, it can still make really powerful predictions about the real world. So we can start off with quite an intuitive picture, like a single particle in a box, and we can actually get from there to predicting, say, the conductivity of copper. And then we can say to students, you can go away and perform an experiment to measure the conductivity of copper, and even though it won't be precisely correct from your prediction, because we have ignored a few things, it will be very, very close. Now, what we can then do is go back to those fundamental assumptions that we made, the things where we sort of had to say to students, you need to just kind of trust us that it's like this, and we can say, what would happen if these assumptions were incorrect? What would happen if we lived in a two-dimensional universe, for example? And then they can see that the result they would get, for example, for the conductivity of a metal, would not just be a little bit different, but would be radically different to the universe we observe.
So I research computational biophysics, so that's using computers to solve physics problems in biological systems. Experimental. So my work involves setting up my own little computational universes in which I can apply physical laws. I can understand what simple systems do, individual particles. I can predict their motion analytically, mathematically, but emergent properties, lots of particles, lots of molecules all interacting together, that's not analytically solvable. That's why we need computer simulations. So I have to gather data from my simulations and analyze them. And that's experimental, that's empirical analysis of data. So experimental. Real. It's real in the sense that it can predict experimental observations, the outcome of experiments. It's real in that sense. And yet, it is within a simulated, constructed universe within a computer. So there are aspects to the model that do not exist in our universe, and there are aspects in the universe that do not exist within my computational models. So in that sense, no, it isn't real. Yes, they change. They change in line with the scientific method. So in my computer simulations, there's data. I analyze that data, use it to make models. Those models predict new data, measure that data, adjust the models, adjust the data. It's that cycle. So I'm going to explain this by a metaphor. I'm going to say, imagine the universe as a building. And scientists collectively are trying to work out how that building is standing. So an experimental scientist will take measurements of that building, and they'll try and control those measurements as best they can. A theoretician is effectively trying to reverse engineer the blueprints of that building. As a computational physicist, so I'll build a test building based on some parameters, some rules, and see whether or not it stands or whether or not it falls. I can turn off aspects of the universe that experimentalists cannot. So I can turn off electrostatics, I can turn off van der Waals interactions, I can turn off temperature, run that simulation, see if the building stands or falls. No, not wrong. Incomplete. So consider a single room in that building. My earlier models might have predicted that that room stands. Experimental observations may have come in that change the overall model, but that room still stands. So the model was not wrong, it was incomplete.
Okay, so let's take an example from the history of science. Newtonian mechanics was, and still is, used to predict the interactions between objects. And it was considered accurate until the late 19th, early 20th century, when new observations that couldn't be described by Newtonian mechanics led to the development of new physical theories that we refer to as special and general relativity. So, given that Newtonian mechanics was superseded by these theories, that raises the question, was Newton wrong? No, Newton wasn't exactly wrong. It's more that Newtonian mechanics was incomplete. So Newtonian mechanics was an accurate empirical description of the world as Newton and his contemporaries observed it. And it's a complete description of reality within the limits that Newton imposed. One of the most important results that came out of general and special relativity that isn't included in Newtonian mechanics is the famous equation for mass-energy equivalence, E equals mc squared. So what does this equation actually mean? Well, in some sense, it's an empirical formula. We have these three measurable parameters: the speed of light that we can go out and measure. We have mass, say the mass of a particle-antiparticle pair, and if we know those things, we can put them into this equation, and then we can predict how much energy will be output from, say, this particle-antiparticle annihilation. But it also represents something that's fundamental to the structure of the universe, an important relationship between three key concepts. But E equals mc squared also doesn't stand alone as an equation. It's part of this huge web of scientific knowledge, and if it is correct, it implies that all of the theories that fed into it must also be in some sense correct. Newtonian mechanics, special relativity, our understanding of energy and mass. So, now that we understand that Newtonian mechanics was a special case of general relativity, and therefore not exactly wrong, just limited, that begs the question, is general relativity also a special case of something even more profound?
Okay, so everybody likes the idea that theory and data can be brought together in some way, that we can kind of incrementally be confident that we've got closer to a true description of reality. But philosophers of science think there's a problem, a worry about that. We call it the problem of underdetermination of theory by evidence. And I'm just going to show you what I mean with a little diagram. Suppose I do this. Let's call these data points. So you've gone out and you've done an experiment, say, and this is the data that you've collected, so you're plotting it. What do you do next? Suppose this. You fit a curve. Now, in some sense, what you're doing there is you're constructing a theory or a hypothesis, which is supposed to, not just fit those data points, but explain it in some way, and also generate predictions, right? So if that's the curve I've come up with, then I might predict that if I gather some more data, the next data point should also fall on that same curve. And the nice thing is that we can do that. We can do an experiment and go, oh, look, we got the result we predicted, and that's going to be taken as justification for this curve being true, right, or being a good guide to reality. Here's the problem. That's not the only curve that fits those data points. Here's another one. Here's another one. Right? They're all going through those data points. What's the problem? The problem is that no matter how many data points I generate, I might always be able to rule out some curves. I might get some more data and then find out some of these curves don't work anymore. However many data points I've got, there's always going to be an infinite number of lines, different shaped wiggles or what have you, that will fit these data points. Now, anti-realists or instrumentalists just accept this problem and they just say, we should give up on the project of identifying the true curve, right? We've got the data, we can't go any further. This line drawing exercise is, of limited value. Realists instead are people that don't want to do that, right? That want to hold on to the idea that science is a guide to truth. What they typically do is say, we're going to rule out some of these curves. We're going to say some of these curves are better ways of fitting the data than others. The important thing that I think needs to be realised is that you can't use the data to decide which curve best fits the data. You can only rule out some sorts of curves by bringing in some sort of extra theoretical criteria, right? What's typically done is that people will appeal to values of some sort. And scientists don't really like to think of themselves as invoking values. They think of themselves as objective and keeping that sort of thing outside of science. But actually, if you don't appeal to something like simplicity to tell you, let's Occam's razor that curve because that one's too complicated. If you don't make that sort of appeal, then you can't reduce this number of infinite curves that fit the data. You're just left with that infinite set. But if you are going to appeal to simplicity, that's not something coming from the data. So you're going to need some way of explaining why this, apparently quite aesthetic seeming principle, what place does that have in your science?
So now let's throw the questions out to you, the students. Together with your tutor and peers, have a think and a discussion about these topics.
If you're struggling, use these questions as a starting point. Which approach do you think is more important for science, empiricism or logical deduction?
What is the goal of the scientific method?
Is there a difference between trusting the conclusions of a peer-reviewed journal versus an opinion piece in a national newspaper? And if so, what are those differences?
We know that this is a bit different to what you might have expected for a physics tutorial. These questions don't have easy answers, so don't worry if you disagree.
And try to think about how you can apply what you discuss to your work as scientists. We'll see you in semester 2.